In the last video, we looked at simple harmonic motion, which is sometimes abbreviated SHM, or if we have an object that is undergoing simple harmonic motion, we can call that a simple harmonic oscillator, or an SHO. In this video, we're going to look a bit at the energy involved in these processes. So let's look at a box sliding back and forth on a frictionless surface. And pretty straightforward analysis here. We are just sloshing back and forth between potential energy and kinetic energy. If it's at a point of maximum displacement, you're going to have all potential energy, elastic potential in this case. And if it's at the point of equilibrium, when the spring force is zero, then you've got all kinetic energy. And obviously at points in between those, you have some of each, as shown here. So we can say that the total energy in our oscillator at any point is the sum of the kinetic energy, 1/2 mv squared, plus the elastic energy, 1/2 kx squared. And if we don't know this for a specific point, it will be hard to solve for the total energy of our system. But if we know the amplitude and we know the spring constant, then when we are all elastic here, we know that this total energy is equal to 1/2 Ka squared, because our displacement is equal to the amplitude. Also, if we know its a maximum speed as it's going through the middle, that is going to be the total energy at that point. So we can have 1/2 mv max squared. So a few different ways at getting at the total energy. And if we take this part of the equation here and solve for velocity, we can get a nice expression of the velocity as a function of the position of our oscillator. In the last video we saw the velocity as a function of time, but sometimes it's easier to figure out how fast it's going just by knowing its location rather than how long the thing has been oscillating and what you call t equals 0 and all of these things. So if we rearrange this guy, we can get rid of the 1/2, so we've got mv squared equals, I'm going to pull this to the other side and pull out the k, so we're going to have k times a squared minus x squared, quantity there. Just divide mass over, take the square root, and you get v is k over m times a squared plus x squared. So that's a nice little expression for finding v as a function of the position x. And we knew previously that the maximum velocity was equal to a times omega, where omega was root k on m. And so if we make that substitution in here, we can pull out, now this is a plus or minus, by the way, because we took the square root. We don't have the direction information necessarily from this, because at the same location it could be heading out or back, but it will always have the same speed. Let me box that guy. Alright, so if we essentially pull out an a squared from this, let me do that up here, so we're going to have plus or minus root k over m times a squared. This becomes a 1, and this becomes an x squared all over a squared. This stuff here, that's root k over m times a squared, which just becomes an a. So this is our maximum velocity. So plus or minus the maximum velocity times the leftovers, which is square root of 1 plus x squared over a squared. So just another way of writing the same idea. Okay, let's look at an example here. We have the same harmonic oscillator that we had in the previous video where we solved for a number of these quantities. Well, we were given a number of them when we solved for other ones. Now we want to find the total energy. So we don't know the maximum velocity right offhand, and we don't know the velocity or at a specific position. So the easiest way to do this is, since we know the amplitude, is to use, and we know k, is to use 1/2 Ka squared. So moving right along, we've got this, and it works out to be 0.098 joules of energy in that oscillator. And we can write the kinetic and potential energies as functions of time So we start out with the kinetic energy, or sorry, the potential energy. So we'll start with that part. 1/2 times 19.6. Now, x, we've got x as a function of time. So if we plug that function in here, then we will have u as a function of time. So it's this whole function here, x equals all that stuff. So 0.1 times cosine of 8.08 times t, and that whole thing is squared, which works out to be 0.098 times cosine squared of 8.08 t. And we would expect this to be the coefficient out in front, because at certain points when cosine is equal to 1, or cosine squared is equal to 1, then all of the energy is potential energy, and so it needs to equal our total energy that we already calculated, right? Now, if we want the kinetic energy as a function of time, we could already guess that coefficient out in front, but we'll go ahead and calculate it anyway. 1/2 mv squared. We've got the mass of 0.3 kilograms, and v as a function of time was this guy here. So we've got negative 0.808 times sine 8.08 times t, this whole thing squared, which works out to be 0.098 sine squared of 8.08 t. Alright, and if you add these two things together, we know that at any time u plus k has to equal our total energy. This wasn't part of the question, but you can obviously see here, you factor out the 0.098, and then you just have cos squared plus sine squared. I'm not going to bother writing the arguments, and that from our trig identity is 1, and so that gives us the same total energy that we had up here. Hooray for consistency. Alright, we want to find the velocity when it is 0.05 meters from equilibrium. So here is where we get a chance to use our new equation. I'm going to leave the plus or minus off and just say that we're finding the speed. So that equation again was k over m times a squared minus x squared. And plug in your numbers, 19.6 over 0.3. A squared is 0.1 squared, 0.05 is our x, and we find a velocity of 0.7 meters per second at that location. This would be a whole lot easier than finding the time it took to get to that location, and then finding the velocity at that time and whatnot. Alright, kinetic and potential energies when we are halfway to our maximum amplitude. So I'll start out by doing the potential energy because it's got x in there rather than v. So that's going to be the easiest way to start. So 1/2 kx squared. K is still 19.6. Our x is going to be the amplitude of 0.1 over 2. And that gets squared. This works out to be 0.0245 joules. Now you could get at the velocity at that location and using this equation, and then plug that into your kinetic energy. But the easier way to do this is to say, well, total energy, as I said here, is kinetic plus potential. So kinetic is the total energy minus the potential energy. We know our total energy, 0.098. Minus 0.0245, so we can find the kinetic energy at that location, 0.0, I guess I have a 0 out in front on the other ones. So there's our kinetic energy, and that's all there is to it. See you next time.